All right, welcome to day 8, everyone. Here are your homework answers. And we're going to pause the video for a couple minutes for you to check those answers. All right, since I don't know which ones you need, I'm just going to talk through all of them briefly. So the first couple we had to find when the absolute value, or the inside, I should say, crosses the x-axis. So we had 3/2 for the first one. When we are left of 3/2, that's when the inside is negative. So that part of the piecewise got negated, the negative 2x plus 3. The other part is the positive part, 2x plus 3. So split up your bounds, do the integrals separately, and you eventually get 4.5. In the x squared minus 4, 1, the only one of the zeros that's on our original interval is the 2. So from 0 to 2, that's when that quadratic's below, so that gets negated. And then from 2 to 3, it stays positive. Do your antiderivative, sub in, and you get 23/3. For 26, we had that 1 and 3 were the roots of that. So between the 1 and 3 is where it dips below. So that's the part that got negated. And then so the 0, 1, and 3 to 4 stayed the original expression. So then do your antiderivatives. You had a whole bunch of subbing in to do. Make sure the second part, when you have the minus, if it's a bunch of terms, you put it in parentheses. So that negative applies to all of them. And then when you combine like terms, we end up getting 4. In 28, 1 minus sine squared is cos squared. Cos squared divided by cos squared is 1. Keep in mind our variable is theta, so antiderivative of that is theta. Sub in your stuff, you get pi over 4. 30, you're just simply doing your antiderivative rules and subbing in. Same idea with 32. For 33, if you multiply the dt over, we get dv as that expression and times the dt. That goes in our integral. And we wanted to know only the first 3 years, even though the depreciation was represented 0 to 5. So this will add up depreciation those 3 years, and we get it's losing $135,000. In 34, it's kind of an interesting situation, but they just gave you the setup already, so you just had to do your antiderivative and then sub everything in. You get 2 over pi. And area between the curve and the x-axis is just your integral. So you're just finding from 0 to pi. This was our picture in case you need the reference of that function. And that would give us the area under the curve, between the curve and the x-axis. For 44, we wanted between this graph, the minus x squared plus 3x and y equals 0, we wanted to be bound like that, by that. Well, this is going to be crossing the x-axis at 0 and 3, so it's going to look kind of like that. So we were looking for the area of this space. So we're essentially just doing our equation and doing it from 0 to 3, and eventually got 9/2 for that. So they told us this area is 1.5, so really that's minus 1.5 if we do the integral, and then the whole thing was going to be 3.5. So in 55, we have negative 1.5. In 56, we need to think of it as negative 1.5 plus what value from 2 to 6 is going to give you 3.5. So essentially negative 1.5 plus what is going to equal 3.5, and that's where the 5 comes from if you add the 1.5 over. Well, the absolute value one, if we flip the 1.5 up, we've now got a 1.5 section, and then the 5 section, because we just found that this area was 5. So together that gives you 6.5 and 57. In 58, It's just -2 times our answer from 55, so we get 3. In 59, we want to separately think of it as our integral of 2 dx plus our integral from 0 to 6 of f of x dx. 0 to 6 of f of x dx we already knew was 3.5 from the question. Well, here, the antiderivative we can just do. It's 2x, and you're evaluating it from 0 to 6, so that'll end up being 12. And when you add the 12 and the 3.5, you get 15.5. You could also think of it visually. 2 is a horizontal line, so the area under the graph of y equals 2 from 0 to 6 is just a rectangle with a base of 6 and a height of 2. Going down to 42. 0 to 6, you would just take the 0 to 3 and the 3 to 6 and add them together, so we get the 3 there in 42a. In b, we do always want the lower bound on the bottom, but if you have to flip them, it negates things. So this will be the same as minus the integral from 3 to 6, so it's just minus the -1, so you get 1. If your bounds are the same, it's just 0, because there's no bottom dimension then in your area. And then from 3 to 6, the -5, you're just multiplying the -1 by -5 to get 5. In 43, you're adding the two parts together to get 8. In b, you're doing the g of x minus the f of x, so -2 minus 10 gives you -12. In c, you're just doubling your g of x, so we get the -4. And in d, you're just tripling your f of x1, so you get 30. All right, in our notes packets, let's just do a quick review of our identities because they tend to come into play. So our reciprocal identities, that's our secant x equals 1 over cos x. You have cosecant x equals 1 over sine x. And cotangent x equals 1 over tan x. Your quotient properties, we got tan x equals sine x over cos x. And we got cotangent x equals cos x over sine x. And I didn't specifically mention, but this should all be in your notes packets. You can be doing that. And then our Pythagorean properties, the main one to remember, you got sine squared x plus cos squared x equals 1. And we get all the others by dividing. So imagine we have that sine squared x plus cos squared x equals 1. If we divided everything by sine squared x, a sine squared x divided by a sine squared x is a 1. A cos squared divided by a sine squared is a cotangent squared x. And a 1 divided by a sine squared is a cosecant squared x. And then if you changed all these sine squareds to cos squareds, a sine squared divided by a cos squared will give us a tan squared x. Cos squared divided by cos squared is 1. And then 1 divided by cos squared will give us secant squared x. And all of those can often be used to replace things in your integral to get you something that we can actually handle. So we are going to work through some of these problems in the notes packet. Many of these are just taken right off of the review sheet. So if you're comfortable with these ones as we're doing them, when you get to those ones on the review sheet to practice for the test, you don't have to necessarily redo them. So in this one here, first we want to recognize that we've got a 1 plus tan squared in the denominator, which is one of our Pythagorean properties we just talked about. So we could rewrite this as secant cubed theta tan theta. And the bottom will just become a secant squared theta, d theta. Well, you can divide out a secant squared, so that's going to equal secant theta tan theta. And take a second, share in your groups what the antiderivative of secant tan was. Some of you said it very loud, and I heard it all the way where I currently am, that your antiderivative of secant tan is just secant theta. And don't forget your plus c on the end. So this would be an example of an of an integral where we've got to do some replacing with our Pythagorean identities. We would call this an indefinite integral because it doesn't have bounds on the integral, and we would need that plus c. If we go over to the next one, we've got a definite integral because it has actual bounds. When looking at this, hopefully the first thing you recognize is the numerator could just be a 1 from our sine squared plus cos squared equals 1. Theta, I guess we have in this case. And then 1 over cos squared is really just secant squared. And you can share within your groups what the antiderivative of secant squared is. And hopefully you said tan theta. And we're going to evaluate that from negative pi over 6 to pi over 3. So we'll be doing tan of pi over 3 minus tan of negative pi over 6. Meaning we're going to need our 30, 60, 90 triangle. Across from 30 is always 1, across from 60 is radical 3, across from 90 is 2. Pi over 3, 180 divided by 3 would give you 60. So tan of 60, you've got opposite is square root of 3, adjacent is 1, so we just get square root of 3. Minus, we've got a negative pi over 6. So that's going to put us in the fourth quadrant, which is the C quadrant, so tangent is negative. So whatever we get from our reference triangle, we'll have minus it. Pi over 6 is 30 degrees. When we do opposite over adjacent, we get 1 over square root of 3, or rationalized is square root of 3 over 3. Minus a minus will give us a plus, so we'll get 4 radical 3 over 3. Going on to the next one. This is a somewhat common AP multiple choice question. We've got our definite integral, and before we had definite integrals, we saw our limit notation set up of what an integral really is. The integral is if we're doing our Riemann sums and adding up those rectangles, letting the number of rectangles approach infinity, whatever that sum is approaching, that's the value of our definite integral. Well, all of them have the limit n approaches infinity. You got your summation, I equals 1 to n. Our basic setup. One part is f of our a value plus delta xi, delta x times I, and then times the delta x. Well, define delta x, that's your change in your x values, or in other words, the base of each of your rectangles in the Riemann sums. You always do b minus a over n. And keep in mind, the a and the b are the values on the integral. A is where the interval starts, b is where the interval ends. So for us, we're going to have 7 minus 3 over n, or in other words, 4 over n. So we're going to have limit n approaches infinity, summation I equals 1 to n. We know this part's going to be 4 over n. The function that we're subbing into is the x squared. So we're going to have something squared. We have the a value, which for us is 3, plus our delta x times I. So we're going to have 4 over n times I. So we're just looking to see which choice matches that, And it looks like it's choice D. They've just got it as 4I over N. B would have been the choice if our function had just been x, because notice it's not squared. C could have been our choice if our interval went from like 0 to 4, because we would have had 0 in the A spot, then plus still 4 over N. And A can't really work out for anything. All right, we want to estimate our area under this from -1 to 3. We're going to use 4 rectangles, and we're going to do a lower sum, so a left-hand endpoint. So this is our Riemann sums. So, just so we can get a visual, well, I guess first let's find our width. We'll do 3 minus -1 over 4 for our B minus A over N. So that'll be 4 over 4, so we get a width of 1. So here's a base of 1. And on the left, we're already hitting the function at 0, so we don't go up at all. Next one, we'll do a base of 1. We'll go up on the left till we hit the function and go over. Next one, we'll do a base of 1. Go up on the left till we hit the function and go over. And the last one, base of 1, up on the left till we hit the function and go over. So we're essentially finding the area of each of these. So we are going to have out front, for our L4, you always have your width first, because that's the base of the rectangle, and then times our heights. Our first height is 0. The second height is 1, and we could have gotten that by putting 0 in for x here. The next height, we're putting, for the green one, we're putting 1 in for x, so it's really square root of 2, because that was not at a nice value. Next one, we put in 2 in for x, we get plus square root of 3. So this doesn't really simplify that much. You have 1 plus square root of 2 plus square root of 3. Now let's say we were to do this on the calculator. We would have had 1 for our width. Then we would have had sum sequence. We would have our function that we're putting into, the square root of x plus 1, comma, whatever our independent variable is in that function, so that'll always be x. Where our interval starts, which was -1. Where our interval ends, which is 3, and the step size in our interval at delta x, so we'd have 1. And 2 parentheses. I think I need 3 parentheses there. Now, this is a no calculator test, so I can't actually have you put it in the calculator, but I could ask what would the command in the calculator be that would allow us to find the sum of this function. So you do want to at least be comfortable being able to tell that. All right, we are going to pause the video for 3 minutes and let you try that bottom one there, the integral of the 3x to the 5th one. All right, should have divided them all by x squared, taken your antiderivative, exponent goes up 1, divide by that new exponent out front, and we have ended up getting choice E eventually. So this next one is essentially a trick question. What we need to notice is that there are no thetas inside our parenthesis there. So that's just a constant. Imagine we had integral of 7d theta. Well, we would just have 7 theta plus c, because the constant's antiderivative would then be something that's linear. Well, this is the same idea, just instead of a 7, we have some messy number, sine 5 minus cos 3. So when we do its antiderivative, it would just be that times theta with a plus c, so we would end up having choice A. All right, next one was like you saw in your homework. We are going to pause the video for 4 minutes and allow you to try that one. All right, two ways you could have done this problem because it's a multiple choice, could be done anyway. It did not say in the directions if it had to be done algebraically or this one could be done with area formulas, so we'll show you both ways. So algebraically, we would see when is the inside equal to 0? It's 0 at 2. When we are left of the 2, that makes it negative inside, so we'd have the negation of that. So from negative 1 to 2, we have the expression negative x plus 2, but then from 2 to 3, we have x minus 2. Do your antiderivatives, sub in your values. Make sure after the minus you put in parentheses because we have multiple terms, so the negative applies to all of them. And then when you combine everything, you end up getting 5. Now, if we were to do this problem in terms of areas, this is what our graph would look like. It's an absolute value. It was shifted 2 to the right. So that's where our point is, that corner point. Well, this just gives us our area under the curve to be 2 triangles. The first triangle, we just have 1/2 base of 3 times height of 3. The other one, we have 1/2 base of 1, height of 1. So this will give us 9/2 plus 1/2, which is 10/2, or in other words, which is 5. So you want to be comfortable doing it both ways. I could give you this question and just leave it as is, and you can do it however you want. I could say that it needs to be done algebraically, and you have to do it like it on the left, or I could say it needs to be done using area formulas, and you'd have to do it like on the right. Alrighty, next one, we want the absolute value of this from 0 to 5. So our negative part is going to be flipped up. So the purple is actually our absolute value graph. It is 2 quarter circles. Because it's an absolute value graph from our choices, we should know that C can't be possible because we're finding all positive area that's above. In this one, we have a quarter circle, so we're going to have 1/2 pi, or sorry, 1/4 pi times our radius squared. Well, that radius there is just this 2. Then for the other quarter circle, we'll have 1/2 pi times our radius squared. Here's our radius here, which is 3. 2 squared is 4, times a fourth is 1, so we get pi. 3 squared is 9, times a fourth, we get 9/4 pi. Well, pi is 4/4, so 4/4 plus 9/4 will give us 13/4 pi. Next one, remember we only have certain antiderivative rules, our trig ones. We've got our power rule, so you got to force things to match those. So we can rewrite this, and using our exponents, we can rewrite it as x to the 3/4 minus 2x, and it would be negative 2/3 because it's coming from the denominator. From there, we'll have x. If we add 1 to the exponent, add 4/4, we get 7/4. Out front, we divide by 7/4, which is the same as multiplying by 4/7. For the next one, add 1, and we now have 1/3. Dividing by 1/3 is the same as multiplying by 3, so we get -6. And then we've got to have our plus c on the end. And if we look through, the only one that's got the -6 is here. And then this is kind of written in a funky way. This is x to the 1 times x to the 3/4. Well, if you add your exponents, that would give you x to the 7/4, so therefore that ends up matching with choice C. All right, I want to move a couple pages ahead to this picture here. So we've got 3.2 for this section, we've got 1.6 for that section, and 4.4. Now the area is 3.2, so keep in mind the integral would be negative that. So we're going 0 to 8, but we've got addition or subtraction going on. So we want to switch this as 0 to 8 f of x dx minus integral from 0 to 8 of 2 dx. Well, from 0 to 8 of the f of x, we can just add up all of our areas there. We've got a negative 3.2 for part A, negative 1.6 for B because it's under the x-axis, plus 4.4. And then for the other integral, we'll have minus. And two ways that you can think of this. You can go ahead and do the antiderivative of 2x and evaluate it from 0 to 8. Or you can think of it as a horizontal line at x equals 2 from 0 to 8. So that's base of 8, height of 2. So either way, you're going to end up getting 16 there. When we combine those first parts, we're going to end up getting minus 0.4. So in the end, we get minus 16.4, or in other words, choice A. And last one that I want to look at is if we go ahead a few pages to this one here that's got the integral of negative 3 to 5. When we go negative 3 to 5, we know that the area is 12. If we go from 1 to 5, we know that the area is negative 5. And we want to know what's the area from negative 3 to 1. Well, the red and the purple should put together to give us the green. So just add your 5 over. So we get that unknown area is just 17. So make sure before the test you end up working through the rest of the study guide. And other than that, if there's any time left in the period, you can work on that study guide and then have a good rest of your day.